thus far, we've done all the legwork to set up finite elements on one reference element. So we can make, we get given reference elements, we can put nodes down on reference elements, we can make a polynomial basis on a reference element, which is what the van der Waals matrix more or less does, and we can put those two things together to get the finite element basis on a element, and we can evaluate it. So we can do individual elements. So now we need to glue individual elements together to get all the elements in a finite element space. And to start with, we've got to get the topology of that right. And then afterwards, we will get the geometry right. And the geometry more or less falls out once you've got the topology right. So what do I mean by that? Well, each element in the mesh maps back to the reference element. And it maps back to the reference element under a geometric change of coordinates, but it also maps back to the reference element in a topological sense, which is to say each vertex of the physical element needs to map back to a vertex of the reference element, each edge maps back and the cell maps back. And they have to map back in a consistent way so that, for example, the vertex, the local vertex 0 will map to some global vertex, and the edge that local edge 0 maps to had better be the opposite edge. Otherwise, you haven't consistently mapped the cell to the one that you were expecting. The reason we need that is because when we do continuity, which you guys have done and we will revisit in a second, we need it to be the case that those basis functions which are associated with the surface of the element actually join up with the basis functions in the next physical element. And that will only happen if the mapping is consistent. So, how do we do this? Well, it's a two-stage process. The first stage, what we need to do is associate the local basis functions with the local topology. So, which basis functions are on edge 0? Then, we need to work out the mapping from the local topology to the global topology. And what that will do is enable you to say, okay, when I visit element 42, which degrees of freedom correspond to the coefficients of which local basis functions on that element. So that's the next bit. We'll probably talk about that tomorrow. Maybe the end of this lecture, but probably tomorrow. Let's worry about the first one first. So that is, how do I associate local basis functions with local topology? So this is the bit where we build stuff up progressively. So the Lagrange element family is globally C0, right? It's in the Sobolev space H1. Being in the Sobolev space H1 requires complete continuity. So that means that for every point in the space, the limits of the function as they approach that point from every direction resolve to the function. So inside each cell, that's trivial. Because inside each cell, we're a polynomial, and polynomials are C infinity, and life is great. So it matters on the edge, and it matters everywhere on the edge. So the first thing we have to do is we have to ensure that at the vertices of the cells, we are still continuous. And for that to be true, it's necessary to associate a basis function with each vertex. Right? If that were not true, then the basis functions for the different elements that touch at that vertex could take different values. And that would give you discontinuity. Whereas if you associate one basis function with that corner, well, that basis function, by definition, will take the same value in all the adjacent cells. And also, all other basis functions will vanish to 0 at that point. So that's enough to get you continuity there. Check. Okay. Is that enough? Actually, no, it's not, because you've also got to be continuous along all the edges. Now, if you are the linear Lagrange space, we're done. And the reason that we're done is on each edge there are 2 vertices. Those 2 vertices have degrees of freedom associated with them, so that nails down the value at each end. And we're a linear element, so the function space restricted to each edge is also linear, and nailing down 2 values is enough to specify all of the linear functions. So if you have a linear edge and you are continuous at both ends, you must be continuous everywhere in between. Job done. It's not true for higher order. So for quadratics, for example, I need 3 points to constrain the edge. I've got 2 because the ends are nailed down. So I need it to be the case that there is 1 more basis function associated with the edge. And that's enough, because now I've got quadratics on the edge, all other basis functions vanish, and life's good. Because I'm not actually insane, my basis function is going to be in the middle, and so both sides will agree on where it is. So actually this continues to work as we go up. So in cubics, I need 4 points, so I need 2 points on the edge. I can put them anywhere on the edge, but the same thing to do is to make it symmetric. They don't have to be equally spaced, and in fact in some respects it's better if they're not, but we are going to use equispaced points because it's easy. We did that in the Lagrange points definition. And now it matters which order they go down in, because if this element thinks that the basis functions go down this way, and this element thinks that they go down that way, then what you get is some weird twisted polynomial space on the end. You won't get a continuous polynomial space. And so it's critical, and we'll look back at this in a second, that the basis functions are laid out in the order of the orientation of that edge, because we've already set things up so that the edge orientation is consistent from both sides. So that's good. And then finally, if you are at least third order, then we'll discover that having associated degrees of freedom with the vertices and the right number along all the edges, we still haven't used up all the degrees of freedom. And where do the rest of them live? They live in the middle. And the thing about that is that because we have fully specified the function space all the way around the edges, the remaining basis functions vanish around the edge. And so they take the value 0 on the edge, they don't connect to the basis functions in other elements. So they're fine. That's easy. If we were doing 3D, then we'd have face basis functions, and the faces touch together, and they have to touch together the right way up. And it's the same principle as edges, just a bit more complicated. So in that argument, how much do I need to put on each edge? Well, the pattern that I just described works out to be p minus 1 choose d. So if the polynomial degree is p, and the dimension is d, this tells me how many to put there. So for example, if the dimension is 2, and the so if the dimension is let me get this right. If the dimension is 2, so it's the face, and the polynomial degree is less than 3, then I'll get none. If it's exactly 3, I'll get 2 choose 2, which is 1. It moves up like that. So if the edge is 1, the polynomial degree is 2, then I get 1 point on the edge. It continues up like that. And in the case where d is 0, then I get 1 no matter what. So that's what we're expecting. So this is how it looks like when you do it. So here is our local topology with the ordered edges. And assuming that you implemented Lagrange points the same way up that I did, this is where your points end up. It doesn't matter, right? It does not matter what order you number these points in. The numbering is completely arbitrary. You'll just get a permutation of the matrix if you use a different ordering. But if you ordered mine, so I ordered mine in lexicographic order, so the x's go up fastest. So they end up in this space. And so for P1, they're all associated with the vertices. For P2, 0, 2, and 5 are associated with the vertices in that order. And 1, 3, and 4 are associated with the edges, except actually that the order is 4, 3, 1, because that's the order the edges go in. And then in this case, I have the slightly more complicated case where I have suddenly got more than one entry on the edges. And so you have to make sure that on this edge, 1 comes before 2, because the edge goes that way, and so on. So if you number them the way around I number them, it turns out that they come out in ascending order. But that's an artifact of the way I numbered the element. It's not an intrinsic property. So you need to make damn sure that what happens for your one works.